Hello my dear students, welcome to IMS Gate Academy Smart Revision session on Communication System subject. So in the last class, that is on yesterday, we have discussed regarding the digital circuit subject, the Smart Revision session. We have conducted in 2 sessions. In those 2 sessions together we have discussed the entire digital circuit subject, which was common for 4 branches: EC, Electrical, Instrumentation, Computer Science. Okay, whoever couldn't watch or whoever couldn't attended that session in live, so you people can watch that particular session in your free time. Okay, so all the 4 branch students, EC, Electrical, Instrumentation, Computer Science, all the 4 branch students will get the good command over the digital circuit subject. So we have covered, right, all the important points and formulas regarding digital circuit subject in 2 sessions. That is on yesterday we have covered, right? Yeah, very good afternoon one and all. So in this particular session, and today we are having one more session, right? In these 2 sessions together we are going to discuss regarding the communication system subject, the for all the chapters, whatever the important points and formulas are there, we are going to cover in 2 sessions today. So whoever watching these 2 sessions completely, they will get the maximum benefit regarding the communication system subject, which is very much helpful for coming GATE exam, right? So this subject is common for 2 branches, EC and Instrumentation. So for EC branch, regarding this particular subject, total we are having 7 chapters. So all the 7 chapters will be there for EC branch, whereas for Instrumentation, out of 7 chapters, only 4 chapters will be there, right? So the first and second chapters will be there, and then third and fourth won't be there, and fifth and sixth will be there for Instrumentation. So out of 7 chapters, only 4 chapters will be there only for Instrumentation, right? So the coming to the weightage of this particular subject, regarding EC, the weightage will be 8 to 12 marks, whereas for Instrumentation the weightage will be 2 to 4 marks. Okay, so in this entire session, and next we are having one more session. In these 2 sessions together I will discuss all the important points and formulas regarding communication system subject. So all of you kindly share this video link and the next upcoming link, right, with all of your friends, so that they also will attend this session, these 2 sessions in live, and they also will get benefited from these sessions. Okay, so before going to start our session, okay, I am going to give 2 important updates. After that I will start the session. So here at our IMS Gate Academy, we are having the live online program for all the GATE 25 and 26, whoever targeting for GATE exam in 2025 or 2026. So for all those aspirants, for all those students, here we at our IMS Gate Academy, we are having live online program. So whoever interested, whoever seeking for the enrollment, right, so kindly share this valuable information to all of your friends and juniors. Okay, so whoever enrolling for live online program, so all the students will get the access of 800 plus hours of live online classes. In addition to that, we are going to provide theory book, exercise book for each and every subject as per your branch. Okay, and not only that, in addition to theory book, exercise book, we are going to provide 30 plus years of GATE question bank. Okay, so this is one of the unique product at our IMS Gate Academy we are offering to all our enrolled students. Okay, so you will get the very great learning when you are referring our GATE question bank, because we have provided for every question the best possible solution, and wherever required we have provided more than one solution, and what are the important points, key notes, everything we have provided. And for typical questions we have provided even video solutions, so that you are getting great learning when you are referring our GATE question bank. And not only that, in addition to that, we are providing 12 my plan sessions for all the enrolled students. Okay, so on every month they can book, each and every student they can book 1 my plan session. Okay, and they can get the proper guidance and study plan from the corresponding mentor. And in addition to that, we are providing 130 plus online tests, right? So for every chapter we are going to provide 1 test, and then for every subject basic level test will be there, advanced test will be there, and then multi-subject test will be there. And after that, for overall subject, for all the subjects together, we are going to provide all new mock tests as well, right? So all those tests together, total we are having 130 plus online tests. Okay, so from our live classes you will get whatever the knowledge required for every concept which is there according to your GATE syllabus. You will get good command over the basics, and not only that, how to solve the questions, right? You will get the method of solving, okay, and after getting the knowledge from attending from our live classes, right, you are getting from exercise book, you can check your confidence level. Okay, and not only that, after that you can refer our gate question bank, and after that you can attempt these tests. So in this way you are getting great opportunity to check each and every concept, whether you are confident or not, or even regarding any method also you can check your confidence level, right? So in this way we are providing whatever is required for your coming gate exam, right? Whoever aspiring for gate 25-26, right? So here at our IMS Gate Academy we are going to provide each and everything. Okay, so whoever interested for live online program to enroll, so kindly book the free counseling session regarding this particular link already provided in the description of this particular video. Okay, and one more important update. So this is our Telegram channel. Okay, link is provided. This link is also provided in the description. So I hope all of you, I hope some of you already joined our Telegram channel. Whoever not yet joined, okay, so kindly join our Telegram channel. So it is free for everyone, right? So if you join our Telegram channel, what are the benefits that you are going to get? Say for example, currently the live session is going on at our IMS Gate Academy YouTube channel, right? So similarly, whenever upcoming events are there in our YouTube channel, so regarding all those sessions updates you will get in this particular group. Okay, and not only that, whatever faculties are explaining whenever the live sessions are there, whatever faculties are writing on the board, okay, on this digital board, whatever we are writing, that particular notes we will provide in the PDF format the right after the moment the session is over. So after the session our team will upload in this particular Telegram channel, right? And okay, and not only that, whenever we are conducting any webinar or seminar, that time you will get the updates related to those webinar and seminar, and whenever the PSU or government job notifications are there, regarding that also you will get the video updates in this particular channel. Okay, and but not the least, on daily basis our faculties will post a quiz question, right? So you people can actually participate and you can choose one among the given 4 choices, whichever is correct, and the very next day, okay, the moment you have attempted the quiz question, you can check whether your answer is correct or not. Okay, if you want to, suppose due to any reason if your answer is wrong, no issue at all, the very next day our faculty will provide the solution for that question. You can go through the solution and you can cross check. Okay, so in this way you are getting great opportunity that on daily basis you are learning one new question like quiz question, right? So it is a great thing. So in this way you are getting so many updates in our Telegram channel. So whoever not yet joined, okay, no issue at all. So in your free time, just kindly join our Telegram channel regarding this link already provided in the description of this video. Okay, right. So I hope all of you are eagerly waiting for the session. So let us start. So the first chapter, that is Introduction and Amplitude Modulation. Chapter 1, Introduction and Amplitude Modulation, which is common for both the branches, EC and IN. Which is common for both the branches, EC and IN. Yeah, I hope all of you are having the awareness regarding the signal frequencies. We can note down. We are having many signals, but among which I am considering 3 signals. One is voice signal, another one is audio signal, and other one is video signal. Voice signal, the frequency range is 300 Hz to 3500 Hz. 3500 Hz, or you can write 3.5 kHz, both are same. Next, regarding audio signal, 20 Hz to 20 kHz. Coming to the video signal, video signal, the frequency range is 0 to 4.5 megahertz. 0 to 4.5 megahertz. So this is regarding signals, the operating frequency range. Okay. Now I will just discuss regarding the Fourier transform whatever the basics are required. I hope some of you already attended regarding signals and system quick smart revision session previously. Okay. Whoever not watched, okay, so kindly watch that particular session in your free time. But here whatever I am going to discuss regarding Fourier transform, few basics that which are going to use in this communication system subject, those properties only I am going to cover now. Okay, right. So regarding Fourier transform, so x of t is the time domain signal, the corresponding Fourier transform we used to represent either x of omega or you can represent in x of f also. Okay, based on the convenience you can follow any notation, no problem. Because ultimately omega, when you are substituting 2 pi f, that function you are getting in terms of normal frequency, that's all. Okay, so regarding x of omega equal to integral minus infinity to infinity x of t into e power minus j omega t dt. E power minus j omega t dt. Okay, similar to this one you will get here x of f equal to same function. You can copy as this integral minus infinity to infinity x of t into e power minus j. In place of omega you can substitute 2 pi f. 2 pi f t dt. 2 pi f t dt. Okay. So this is regarding Fourier transform, either in the omega form or in the normal frequency f. Okay. Now whenever you are having x of omega, okay, if already x of omega is there available, then you can calculate x of t. You can calculate x of t by applying inverse Fourier transform. By applying inverse Fourier transform, regarding that the formula you will get 1 by 2 pi integral minus infinity to infinity x of omega. Here e power minus j is there. Now you will get e power plus j. E power j omega t. Here you are getting, you are performing the integration with respect to t. Now you have to perform integration with respect to omega, d omega. Right. Now omega is nothing but what? 2 pi f. Omega equal to 2 pi f. So if you perform differentiation, then what you will get? 2 pi is constant, you will get df. 2 pi is constant, you will get df. Right. Now in place of d omega, when you write 2 pi df, okay, then 2 pi will get cancelled, you are getting df. Right. So that means here you can write x of t in terms of x of f. X of t equal to integral minus infinity to infinity capital X of f into e power, here minus j, here plus j, e power j 2 pi of t df. See, if you are using the Fourier transform relation like this, you have to take care about this 1 by 2 pi. Okay, suppose if you are following this relation, here no need of that 1 by 2 pi. Okay, here you are getting minus j, here you are getting plus j, that's all. Okay, so for the timing I will follow this convention. I hope some of you might have followed this convention while you are studying signals and system. Okay, no problem at all. That is the reason I have given both the relations here so that you can correlate. Okay, regarding the Fourier transform, in both the equations same. Regarding the inverse Fourier transform, you are getting 1 by 2 pi here. The moment in place of omega, when you have substituted 2 pi f, from there 2 pi will get cancelled, you are getting df. Okay, right. So this is about Fourier transform in terms of omega, in terms of normal frequency f. Okay. Now let us see the properties of Fourier transform. Properties of Fourier transform. So for the timing I am considering x of t is the time domain signal. The corresponding Fourier transform is, For the timing, I am considering the normal frequency x of f. Okay. So regarding the time domain signal, if there is a time shift, okay, x of t minus t naught or x of t plus t naught. So here we are having time shifting operation we are performing, right? So here regarding x of t minus t naught, you will get e power minus j 2 pi f into t naught into x of f. Similarly here plus t naught is there, accordingly you will get plus e power j 2 pi f t naught into x of f. Okay. So when you are having time domain signal, the corresponding Fourier transform is x of f. If you are performing t minus t naught means you are performing right shift operation, right? So that time whatever minus t naught is there, that one will come here, e power minus j 2 pi of t naught into x of f. If you are having x of t plus t naught, then accordingly you will get e power j 2 pi of t naught into x of f. Okay. Now exactly opposite manner you will get for frequency shifting. Next one is frequency shifting. So regarding time shifting, minus t naught, here minus t naught, here plus t naught, here plus t naught. Okay. Now there will be slight change. Regarding frequency shifting, suppose first I am considering x of f minus f naught, just like here. Similarly other one is x of f plus f naught. Earlier for minus t naught, same minus t naught, but here minus f naught is there, so you will get positive. If minus is there, here positive. If plus is there, here negative, like that. Okay. So here you will get e power j 2 pi f naught into t x of t. E power j 2 pi f naught t x of t. Similarly here e power minus j 2 pi f naught t into x of t. Okay, you can remember for time shifting operation, exactly opposite way for frequency shifting. Okay, for frequency shifting operation. So here if you observe regarding these two, okay, you are getting e power j 2 pi f naught t x of t plus here e power minus j 2 pi f naught t x of t. Okay, just perform the addition of these two and then divide with 2. Okay, just perform addition of these two and divide with 2. Same operation you can perform on the corresponding Fourier transform also, right? So from there what you will get? You will get the property regarding modulation property. So e power j 2 pi f naught t plus e power minus j 2 pi f naught t by 2 into x of t. So e power jx plus e power minus jx by 2 is nothing but what? Cos x. So here 2 pi f naught t multiplied with x of t. So regarding this one, the Fourier transform, you have to add these two and divide with 2. Okay. So x of f minus f naught plus x of f plus f naught divided by 2. X of f minus f naught plus x of f plus f naught by 2. So that means what is your observation? Here you are having the time domain signal. You can consider like message signal. Okay. So here you are having cos 2 pi f naught t. That is like carrier signal you can consider. Okay. When you are multiplying the message signal with the carrier signal. Okay. So regarding x of t, you are having the frequency or frequency spectrum, right? It is centered around 0 frequency, say for example, because generally the low frequency signal or baseband signal we will consider for message. Okay. Because the message signal exists in the low frequency range, that is called baseband signal. Okay. Now when you are multiplying with the very high frequency carrier signal, what is happening? whatever x of t spectrum, that is x of f is there, that is going to shift towards right hand side and similarly going to shift towards left hand side by f0 units, okay. So this particular property is called modulation, okay. So this property of the Fourier transform we are going to use in the first chapter of our n-log communication subject. That is the reason we are calling this particular property as modulation property, okay. Here in the time domain we are multiplying the message signal with the carrier signal, but the corresponding frequency spectrum is getting shifted towards right hand side by f0 unit, towards left hand side by f0 unit, but after that overall spectrum is getting scaled by a factor of 1/2, okay. If you want to get normal, you can multiply once again with 2, from there you will get x of f, like that, okay. But whatever spectrum here is there, that is getting right shift and getting left shift, okay, right. So these are the important relations and properties regarding Fourier transform that we are going to use in this particular chapter. That is the reason I have discussed, okay. Remaining all the Fourier transform properties, etc., you people can watch the smart revision session regarding signals and system subject, which already happened in our IMS Gate Academy channel. So kindly watch that session in your free time, whoever not watched that session, okay. Yeah. So next one, need for modulation. I hope by this time all of you are aware of why we are doing modulation in our entire communication system subject, okay. So the first need is to reduce the antenna height, okay. And one more reason why we are using modulation, because whatever the channel you are having, in that channel we want to transmit multiple signals, okay, with the help of multiplexing concept, okay. The same channel is there, but we are going to transmit multiple signals, okay. In order to effectively utilize the given channel, we can use the multiplexing concept. For that also we are using the modulation concept, okay, for multiplexing. Okay, so these are the two main reasons why we are doing the modulation, okay. So in simple words, even from here you can observe modulation means whatever the low frequency signal we are having, we are shifting to high frequency zone, okay. Demodulation means whatever the high frequency signal is there, we are converting back into low frequency signal, okay. So in simple words you can write down, modulation means converting low frequency signal to high frequency signal. Converting low frequency signal to high frequency signal, whereas demodulation means reverse conversion, reverse process. Demodulation means converting high frequency signal to low frequency signal. Okay. So regarding in this entire subject, okay, we used to represent, okay, few terminology or notations. So for easy understanding you can note down, m of t is the message signal, and m of t is the message signal, or we can say it is a baseband signal. Baseband signal means we already mentioned the signal spectrum exists in the low frequency region, okay. Baseband signal. Next, C of t is the carrier signal. C of t is the carrier signal. So this carrier signal we can represent suppose I am considering in terms of cos. If you want, you can consider in terms of sin, no problem. AC cos 2 pi FCT plus phi. AC cos 2 pi FCT plus phi. Okay. So here you can observe, whenever you are having cos signal or sin signal, okay, it will be having the amplitude. Okay, here amplitude of the signal is AC and it is having the frequency FC and it is having the phase angle phi. Okay, so here regarding the carrier signal, we are having three parameters. One is carrier signal amplitude, another one is carrier signal frequency, another one is carrier signal phase angle, right? So regarding the message signal, okay, how the message signal amplitude varies, okay, with respect to that, if you are varying only the carrier signal amplitude, the other two if you are keeping constant, then whatever the modulation we are doing, that modulation we will call it as amplitude modulation. Similarly, if you are varying only the frequency of the carrier signal, if you are keeping other two are constant, okay, in accordance with message signal, only if the frequency of the carrier signal varies, then accordingly we are calling it as frequency modulation. Okay. Similarly, if you are varying the phase angle of the carrier signal in accordance with the message signal, then we will call it as phase modulated signal. Okay. So here one important note point, regarding the carrier signal, you are having three parameters, out of which at any time you are varying one parameter in accordance with the message signal. That time you are keeping other two are constant. Okay. So here whatever the cos signal I have considered, okay, for easy understanding I am representing like this: AC into cos of theta of t. AC into cos of theta of t. AC is amplitude as it is. This entire term I have represented as theta of t. Okay, so theta of t means what? It is like angle term. So accordingly we can call it as angle modulation. Okay. So regarding FM and PM, that means frequency modulation, phase modulation, together we can call it as angle modulation. So in the second chapter we will discuss about frequency modulation, phase modulation, whereas in first chapter we will discuss regarding amplitude modulation and then other modulation techniques regarding amplitude. Whereas regarding the angle modulation, that is frequency modulation, phase modulation, we will discuss in the second chapter. So overall if you observe whatever these three together, okay, if you consider this entire thing is like analog communication system. Okay, with respect to transmitter section, in the transmitter section we will do the modulation, whereas in the receiver section we will do the demodulation. Okay, so in the third chapter we will see regarding the receiver's part. Okay, receiver's part. So that means the first chapter, second chapter and third chapter together we can say it is like analog communication system. Okay. Right. So first let us see regarding amplitude modulation. So regarding the time domain signal, you can write down S of t equal to AC into 1 plus Ka m of t into cos 2 pi FCT. So here you can observe, just like earlier carrier signal, AC into cos 2 pi FCT, same thing, but in addition to that, if you observe closely, you are getting AC into 1 plus Ka m of t. So that means now you can observe that here the modulation is happening with respect to what? With respect to the message signal carrier, right? With respect to message signal amplitude, the carrier signal amplitude is varying, right? So for the timing I have considered phase angle as 0. Okay. Now you can multiply AC into cos 2 pi FCT and other term with cos 2 pi FCT. So from there you will get AC into cos 2 pi FCT plus AC Ka m of t into cos 2 pi FCT. AC Ka m of t into cos 2 pi FCT, where Ka is what? Amplitude sensitivity. So suppose for the time being assume that m of t equal to am cos 2 pi fm into t, am cos 2 pi fm into t. Just like the carrier signal, message signal, we have assumed cos, am cos 2 pi fm into t. So from there what you will get, s of t equal to, the first term you can copy as it is ac cos 2 pi fct plus you can observe here ac ka into am. Okay, ka into am we can write as mu. Okay, I am writing here ka into am, we can write it as modulation index mu. Okay, so that means k into am you are getting mu. Here ac is there. Okay, ac mu, then cos 2 pi fct into cos 2 pi fm into t, right? So you are getting like 2 cos a cos b, but here in the numerator you don't have 2. Okay, so I am multiplying and dividing with 2. Then 2 cos a cos b is nothing but cos sum plus cos difference. Okay, so I am directly writing the direct step. So cos sum, that means 2 pi into fc plus fm into t. Okay, so you will get one more term. Same, ac mu by 2, into cos 2 pi into fc minus fm into t. 2 cos a cos b is nothing but cos sum plus cos difference. Now you can observe, here you are having, see, when they are giving the time domain equation of am signal, okay, you can observe that, okay, if you are having three terms like this, okay, you are having one term which is having the carrier frequency, component. Okay, so other two, if you observe, one term you are having fc plus fm, that means it is upper sideband. When compared to fc, this value is greater, right? So this means this is related to upper sideband. Okay, and similarly when compared to fc minus fm is what? Lower side. So you are getting lower sideband. So that means here in this particular equation, if you observe, you are having the carrier frequency component, and you are having upper sideband frequency component, and you are having lower sideband frequency component. That means two sidebands are there, along with that carrier also is present. So that is nothing but amplitude modulation. The other name of this one is double sideband with carrier or double sideband full carrier. So in some questions they will specify in short double sideband with carrier or double sideband full carrier. That is nothing but the standard AM signal. Okay. So now one more important observation. Here one observation I have told with respect to the frequency terms. Okay, when you are having three terms like this, among these three frequencies, whichever is larger, that will be upper sideband, whichever is the smaller, that will be LSB, and whichever is the in between. Okay, so that will be the carrier frequency. This one important observation. And one more important observation with respect to amplitudes. Regarding upper sideband and regarding lower sideband. You will be having the same amplitude. Okay, whatever the time domain equation they have given. Okay, when you are having three terms, okay, among those three terms, whichever two terms are having the same amplitude, those two terms are related to the upper sideband. Whatever the leftover term or different amplitude you are having, that will be related to the carrier. So in that way also you can guess. Okay, one approach I have given with respect to frequency, another approach I have given with respect to amplitude. Okay, so this is regarding time domain equation. The same time domain equation, if you are representing, say for example, if you are applying Fourier transform, I hope all of you know that whenever you are having cos signal, when you apply Fourier transform, you will get two impulses. Okay, one impulse you will get on the positive frequency axis, another impulse you will get on the negative frequency axis, right? So that time what will happen, whatever the amplitude here you are having, regarding the impulse, the signal strength will become half. Okay, so here I am writing the signal strength of impulse. Okay, signal strength in the frequency spectrum. Okay, in frequency spectrum, the signal strength of the carrier signal will be AC by 2, whereas either at upper sideband or lower sideband, you are going to get Okay, either at upper sideband or lower sideband, you are going to get AC mu by 2 already you are having, once again divide with 2, from there you will get AC mu by 4, AC mu by 4. So, in this way, from the frequency spectrum also, at the upper sideband and lower sideband, you are having the same signal strength, but that signal strength will be AC mu by 4. Okay, with respect to time domain, that signal amplitude will be AC mu by 2. Okay, similarly here, regarding carrier, in the impulse or frequency spectrum, the signal strength is AC by 2, the corresponding time domain signal amplitude is AC. Okay, why we are getting half here? The reason is very simple, because when you draw the Fourier transform, okay, when you apply Fourier transform, when you draw the spectrum on the frequency axis, you are representing the signal spectrum on both positive frequency axis and negative frequency axis. Okay, but in general, practically, theoretically we are drawing the spectrum on the both the frequency axis, that means positive frequency axis, negative frequency axis, but practically the frequency value never be negative. Okay, only for symmetrical purpose, just while we are drawing the diagram, we are representing on both sides. Okay, since we are representing the signal strength on both the frequency axis, positive axis and negative axis, that is the reason you are getting half. Okay, the other half you are getting on the negative frequency axis. But if you are combining both, that means at that particular frequency you are getting the net resultant amplitude is whatever you are getting with respect to time domain, the same thing is going to applicable. Okay, so coming to the bandwidth of AM signal, so here among these three frequencies, this is the maximum and this is the minimum. When you take the difference of these two, FC will get cancelled, FM minus of minus FM, that means you will get 2 FM. Bandwidth equal to 2 times maximum frequency of the message signal. Okay, so coming to the power required for transmitting this AM signal. Okay, for transmitting this AM signal, so here you can observe here. See, all these three terms are what? In terms of cos only. Okay, whenever you are having cos term, okay, so I hope all of you know how to calculate the power. Okay, so power is nothing but whatever the peak value you are having, okay, just perform square and then divide with 2. That means you are taking RMS value, okay, RMS square. Okay, AC square by 2, similarly here AC square mu square by 4, like that, AC square mu square by 4. So when you are adding all of them, from there you are getting the resultant answer like this. Directly I am writing PT equal to the power required for transmitting AM signal is equal to PC into 1 plus mu square by 2. 1 plus mu square by 2. Okay, so if you want, you can split this PC term for both. From there you will get PC plus PC into mu square by 2. Okay, so here PC is the carrier power. Here PC is the carrier power, whereas the other term PC mu square by 2 is the total sideband power. Total sideband power. Total sideband power. Okay, next one you can write down modulation efficiency. Modulation efficiency eta equal to, here the message signal or information you are having in the sidebands, right? So that means the total sideband power, but for transmitting the message signal we are using the help of carrier signal. So the net power required is PT. Net power required is PT. Okay, so the total sideband power divided by the transmitted power. So here you can substitute the total sideband power is this one, PC mu square by 2 divided by PC into 1 plus mu square by 2. So when you do the calculation, from there you will get mu square by 2 plus mu square. Substitute and do the simplification. From there you will get mu square by 2 plus mu square. Okay, so just make one tabular form regarding various mu values. Let us represent the corresponding eta. Okay, suppose if you are having mu value 1, eta you will get 33.33%. Okay, so mu value if you are having 1 by root 2, then the percentage of eta will be 20. Similarly, if you are having mu value 1 by 2, then accordingly you will get 11.11 percentage. 11.11 percentage. Okay. So if you are considering modulation index value 1, then you are getting 33.33% efficiency. Okay, right. So here we already represented K into AM equal to mu, right? K into AM equal to mu. So from here, okay, from this equation, when you consider m of t equal to am cos 2 pi fm into t, so K into am equal to mu, okay. So mu cos 2 pi fm into t into cos 2 pi f c t. Okay, I'm discussing one more equation. See, one equation is like this. Okay, one more equation I'm giving. This equation you got after doing the splitting, right? Before splitting, okay, what is the equation you are getting? I am writing once again. So whilst you are solving the questions regarding amplitude modulation based on the given question in which form they have represented, accordingly you can correlate. Okay, you don't need to remember all the equations. You can remember the starting equation, and after that, according to the given question, you can derive, or you can get, or you can correlate whatever the given equation is there. In that form, you can try to get your standard equation. Okay, right. So S of t equal to here AC into 1 plus K into m of t, okay, where K into m of t is am cos 2 pi fm into t. K into m equal to modulation index mu, then cos 2 pi fm into t into cos 2 pi fct, So this is the signal you are having after performing amplitude modulation, right? So in that amplitude modulated signal, okay, if you consider this is the peak envelope, of the signal. Okay, just like when you are having AC cos 2 pi fct, the peak amplitude is nothing but AC. In the similar way, the peak amplitude or peak envelope of this particular modulated signal is nothing but this one. Okay, so in this peak envelope of the amplitude modulated signal, okay, so from there you can get Vmax, and from there you can get Vmin. How we can get the maximum value and minimum value? By considering here regarding cos term the maximum. Suppose cos term maximum is what? Plus 1. Then you will get AC into 1 plus mu. Similarly, when you consider cos term minimum value, that is minus 1, right? So that time you will get AC into 1 minus mu. Okay, you can do component and dividend rule. Okay, after that you will get regarding modulation index, the formula is Vmax minus Vmin divided by Vmax plus Vmin. Vmax minus Vmin divided by Vmax plus Vmin. Similarly, if you perform addition and then divide with 2, from there you will get AC, carrier signal amplitude AC. AC equal to Vmax plus Vmin divided by 2. Just you have to take the average of the maximum voltage and minimum voltage in order to get the carrier signal amplitude. Or in other words, you can observe when you are performing the amplitude modulation, okay, so the peak amplitude you are going to get AC into 1 plus mu, and the minimum value you are getting AC into 1 minus mu. In between you are having AC, like that. So now you can observe with the help of here how the amplitude modulation is happening with respect to your carrier signal. Okay. So here we are having the formula with respect to power. So similarly you will be having the formula with respect to current. So power equal to I square into R. Okay, so here you will write I square into R, here also you will write I square into R. Accordingly RR will get cancelled. After that you can apply square root on both sides. Okay, so from there you will get IT equal to IC into square root of 1 plus mu square by 2. So here IC is the carrier current, IT is the transmitted current. Okay. So in general, if it is a single tone modulation, they will give one modulation index. Okay. But if the signal is having multiple frequencies, okay, regarding the message signal, then accordingly you will get multi-tone modulation. Okay, so that time generalized case I am writing mu t square equal to mu 1 square plus mu 2 square and so on up to mu n square. For multi-tone modulation, you will be having multiple modulation indices. You can perform square of each modulation index, and then whatever the overall value after performing addition, you are getting, just perform under root. From there you are getting the resultant modulation index. Okay, so this is about amplitude modulation. What are the important formulas are there that we have discussed. Okay, now you just write down regarding generation of AM signal. Regarding generation of AM signal, we are having square law modulator. Whereas for demodulation, of AM, we are having square law demodulator and then envelope detector we are having, and any guess what is the one more? In general, the square law demodulator and envelope detector we can use for modulation index less than or equal to 1, so that we can extract the message signal after from the modulated signal. After, with the help of any of these two circuits, you can get the message signal. Okay, whereas with the help of synchronous detector, you can extract the message signal, okay, whatever the modulation index. Okay, while you are performing the modulation, amplitude modulation, whatever the modulation index, you can easily extract the message signal. So for that case, we will use the synchronous detector. Okay, so here in this entire subject, if you observe most of the cases regarding demodulators or detectors, the best detector is synchronous detector. That is the reason in most of the cases, in order to get back the message signal from the modulated signal, we will use synchronous detector. Okay, but only one problem will be there. Okay, that is quadrature null effect. Okay, here in the amplitude modulation, there will be one drawback. If you are using synchronous detector, quadrature null effect. That means whatever the carrier signal you have used in order to get the modulated signal, okay, at the transmitter section you have used the carrier signal, and at the receiver, in order to get back your message signal from the modulated signal, you are using once again the carrier signal. But among these two carrier signals, if there is a phase shift, and if that phase shift is 90 degrees, that time you are completely losing the information. That means you are not able to get the message signal. That is the reason we are mentioning it as null. Null indicates what? 0. If there is a 90 degrees phase shift between the carrier signal of the modulated signal regarding the carrier signal in the modulated waveform and the carrier signal that you are using at the receiver, if there is a 90 degrees phase shift, that time you are completely losing the information. Other than that, you will get the output. Okay, suppose if there is a phase shift, then you may get the attenuated output. After that, you can pass that output through an amplifier which is having the gain reciprocal of that particular attenuation, so that from there you can extract the message signal actual information. Okay, so here coming to the AM, the main drawback, if you observe from here, modulation efficiency. Okay, so here you can observe you are getting 33.33%, right? So that means what? Here if you are transmitting, suppose 100 watt if you are using, out of which 33.33% or I can say 33.33 watt is there for the message signal or sideband power. The remaining, okay, if you are making approximation like 33 watt, okay, the remaining 67 watt you are giving for carrier. Okay, so it is consuming more power, right? So now we will suppress this carrier so that we are saving most of the power. Okay, or in other words we can say whatever the power that is required for transmitting signal, the entire power we are giving for the two sidebands, okay. So then accordingly the name of the next modulation technique is double sideband suppressed carrier, double sideband suppressed carrier. So here we are completely suppressing the carrier, okay. That means entire power we have given to only sidebands, okay. So here in this case the carrier power is 0, the transmitted power is equal to the total sideband power, okay. So eta efficiency equal to the message signal power, that is total sideband power divided by the transmitted power. Since total sideband power and transmitted power both are same, so in this case you are getting 1, so that is nothing but 100%. So just see the beauty of this particular technique. With the help of amplitude modulation, for modulation index value 1 we are getting at max 33.33%. The moment you have suppressed the carrier power, okay, the moment you have suppressed the carrier power, we are getting 100% modulation efficiency, okay. So now you can correlate, from here. See, this is the time domain signal regarding AM. Now, okay, after you are splitting like this, we have suppressed completely carrier term, okay, that means the first term we have removed, right. Now second term you are having, okay, in that second term if you observe, m of t is nothing but message signal and AC cos 2 pi f c t is nothing but carrier signal, and for easy understanding, okay, you can construct Ka value like 1, then you are getting what, m of t into c of t, just product of message signal and carrier signal, okay. So here s of t equal to c of t into m of t or m of t into c of t, any format you can write, just it is a product of message signal and carrier signal, just product of message signal and carrier signal, okay. So regarding message signal you will be having the frequency FM, regarding the carrier signal you will be having the frequency FC like AC cos 2 pi f c t, AM cos 2 pi FM into t, okay. So regarding this we already seen, you can observe here in the modulation property itself we have mentioned, you can observe here x of t is like message signal, FM you can consider, okay. Here this is the carrier signal, now it is getting shifted, right. So that means here you are getting two frequency terms, right. One is addition of two frequencies and other one is subtraction of those two frequencies, right. So from here you can write, here, or otherwise even from here also you can observe, okay. Just you can observe from this part of the second term, you are getting two frequency components, one is FC plus FM, another one is FC minus FM, right. So here from here together you are getting two frequency components, FC plus FM, another one is FC minus FM. So but there is no, at the carrier frequency there is no signal strength, okay. That's why we are calling it as double sideband suppressed carrier. So bandwidth will remain same, that is 2FM, because the spectrum exists from this frequency to this frequency, okay. Range of frequency is same, okay. In between, in the earlier case at FC also you are having signal strength, but here at FC we are completely eliminating the signal strength, okay. So now with this understanding, okay, so from this formula you can remove the PC term, that means carrier power. So from here you are getting PC mu square by 2, that is the total power required for transmitting DSBSC signal. So PC into mu square by 2, okay. So here PC is nothing but, okay, this is one formula you can easily remember, okay, and I am just giving one more approach also, okay. So regarding PC you can write it as AC square by 2 into mu square by 2, where mu is nothing but Ka into AM whole square divided by 2, but Ka value we have considered 1, okay, in order to get the standard equation like this, right. So here denominator you are getting, okay, 4, and numerator you are having AM square, okay, AC square AM square by 4, or otherwise you can write AC square by 2 into AM square by 2. See, for easy understanding I am just giving the correlation. Here regarding the carrier signal you are having AC cos 2 pi f c t, regarding that power is what, AC square by 2. Similarly here message signal power is AM square by 2. Since here product of the two signals, okay, in the time domain, the corresponding powers if you multiply, that is nothing but the total power, that's all, okay. whatever I have discussed here, this even applicable if you are solving any question with respect to network theory or any other subject. If you are having two sine signals or cos signals, or maybe combination of one signal is sine, another signal is cos, okay, like that, whatever might be you might be having, okay, so that time, okay, you can apply this particular concept. From there also you will get the same answer. Okay, so here basically if you observe, the time domain signal of DSPSC is just product of message signal and carrier signal. So that means here in order to produce the DSPSC signal, we will use the product modulator or balanced modulator. Okay, so here regarding generation of DSPSC signals, regarding generation, we are having first one is balanced modulator and the other one is ring modulator. First one is balanced modulator and other one is ring modulator. Okay, so here ultimately you are getting the output signal is just product of the message signal and carrier signal. That is the reason, okay, any particular circuit or modulator which is just providing the output as product of those two input signals, message and carrier, so accordingly we can call that particular circuit as product modulator. In simple words, we can call it as product modulator. In simple words, we can call it as product modulator. So this product modulator is the word with respect to our technical, okay, regarding our communication system subject. So in simple words, the other name of this one you can call it as multiplier. Multiplier. It is just producing the product of two inputs, that's all, right? Multiplier. Okay, so coming to the demodulation, as we already mentioned, we are using synchronous detector. Regarding demodulation, synchronous detector. So just like the earlier, here also there will be quadrature null effect. Okay, so this is the advantage of DSPSC when compared to AM. But see, with respect to the power required, we are able to reduce, but coming to the bandwidth, still it remains same. Okay, whatever the bandwidth we got for AM, the same bandwidth. Now if you closely observe, while we have discussed regarding time domain signal of AM, here we already mentioned that regarding upper sideband and regarding lower sideband, you are having the same signal amplitude. That means here you can observe that the signal, whatever the message signal you are having, yeah, thank you electrical, yeah, for sharing your experience regarding our classes. Yeah, so here you can observe both in the upper sideband and lower sideband, you are having the same signal amplitude, right? So that means the same information related to your message signal, the same information you are having here. So that means if you want to transmit the message signal, either only upper sideband or only lower sideband is sufficient. Okay, no need to transmit both the signals, right? So that is a technique. Okay, so that means, say for example, when you are transmitting upper sideband, you are suppressing carrier and you are suppressing lower sideband. Or if you want to transmit lower sideband, you are suppressing carrier and you are suppressing upper sideband. That means whatever the next modulation technique we are going to study, that is nothing but we are transmitting only single sideband. Okay, so that means we are suppressing the carrier, right? So single sideband suppressed carrier. Okay, so the next modulation technique is SSBSC, single sideband suppressed carrier. So here we will transmit either FC plus FM, that means upper sideband, or we will transmit only the lower sideband frequency component, Fc minus Fm. Okay. So for generalized case I am writing like this, S of t equal to whatever the equation earlier you got from here. Yeah, here mu is nothing but what? Ka into Am. Ka we have considered 1, right? So that means Ac Am by 2 cos 2 pi into Fc plus Fm into t, or cos 2 pi into Fc minus Fm into t. So generalized case I will put plus or minus Ac Am by 2 Ac Am by 2 into cos 2 pi into Fc plus or minus Fm into t. Fc plus or minus Fm into t. Okay. Now, if you are expanding further, like cos A plus B formula, okay, so cos A cos B, so here I am writing ACM by 2 as it is, cos A plus B equal to cos A cos B, cos A cos B minus, if you are having plus, you will get minus, okay, if you are having minus, you will get plus, cos A plus B equal to cos A cos B minus sin A sin B. If you are having cos A minus B, cos A cos B plus sin A sin B, okay, sin A sin B. So sin 2 pi Fc t into sin 2 pi Fm into t. Okay, right. So if you are having like one equation like this, you can represent either plus or you can represent minus. But if you are expanding like this, you will get two terms. You will get two terms. Here in this case, if you are having minus sign, here in this case if you are having plus sign, that will represent upper side band. When you are expanding that one, here you are getting minus sign because of trigonometric equation, right? So here minus sign indicates same upper side band, whereas here minus sign indicates lower side band, here plus indicates the lower side band, lower side band. Okay, this is for single tone modulation. For generalized case, if you want to represent, you can write like this, S of t equal to Am into cos 2 pi Fm into t, you can consider like m of t. Okay, so here AC cos 2 pi Fc t, so that means AC by 2 cos 2 pi Fc t into m of t. Okay, so AC by 2 into m of t cos 2 pi Fc t, then minus plus. Similarly, AC by 2 you can copy as this, then m of Am cos 2 pi Fm into t you are having, okay, that signal if you are passing through minus 9 degrees phase shift, okay, so from there you are getting Am sin 2 pi Fm into t, Am sin 2 pi Fm into t. So that means here I am representing as m cap of t, where m cap of t is a signal which you are getting from the message signal only after passing through minus 9 degrees phase shift. Okay, after that regarding sin 2 pi Fc t you can copy as this. This is a signal for generalized case regarding SSBSC signal. Okay, so in order to get minus 9 degrees phase shift, you can use Hilbert transform concept. Okay. Now in this case, the total power required for transmitting the SSBSC signal, okay, so is nothing but only one of the sideband power, right? See, this is the total sideband power. Now just make into half. You will get that power you are going to get in any one sideband, right? Pc mu square by 2 divided by 2 is nothing but Pc mu square by 4. Pc mu square by 4. So just like earlier, I am giving one more approach. Pc is nothing but AC square by 2. Mu is nothing but Ka into Am, but here Ka we have assumed 1. So from there you are getting Am square, and denominator you are already having 2. Okay, this 2 I have represented here. So from here you are getting AC square Am square by 4. AC square Am square by 4. Yeah, sorry, Pc into mu square by, here by 2 you are having, Pc into mu square by 2 you are having, once again divide with 2, from there you will get 4. Okay, just one second. here you will get 4. So here 4 2s are 8. So AC square into AM square by 8. Okay, next one regarding generation. Generation of SSBSC signal. We are having two methods. One is frequency discrimination method. Frequency discrimination method. Or another name we can call, since we are discriminating the frequency, we can call it as filter method. Filter method. Okay, so other method is phase discrimination method. Phase discrimination method. So with the help of these two methods, we can generate the SSBSC signal. Coming to the demodulation, as usual, synchronous detector. Regarding demodulation, we are having synchronous detector. But here one more advantage. Earlier in AM or DSBSC, there is a problem when you are using synchronous detector, quadrature null effect, whereas here there is no quadrature null effect. There is no quadrature null effect in SSBSC while you are performing the demodulation. Okay, because you are getting two terms like this, right? So that is the reason. Either you may get this term or you may get that term. There is no quadrature null effect. Okay, and here if you observe, with respect to SSBSC signal, okay, since you are transmitting only one sideband, either upper sideband or lower sideband, so here bandwidth of the SSBSC signal you are getting FM, bandwidth you are getting FM. So when compared to AM or DSBSC and SSBSC, in SSBSC you are getting less bandwidth. Okay, so that is one of the main advantage. And with respect to power also, among AM, DSBSC, SSBSC, in SSBSC you are getting less power, right? And in fact, regarding while you are performing demodulation also, there is no quadrature null effect. So in this way, all advantages only you are getting with respect to SSBSC. Okay. Yeah, next topic regarding this chapter, so that is multiplexing. So here the word multiplexing means we are transmitting multiple signals in the same channel in order to effectively utilize the given bandwidth. Okay, so for that we are effectively utilizing. Coming to that multiplexing, okay, so we are having in this entire communication system subject, with respect to gate exam point of view, we are having two types of multiplexing. One is time division multiplexing, TDM, and another one is frequency division multiplexing. So time division multiplexing means we are doing the multiplexing operation on time share. Okay, on time share basis we are doing, whereas frequency division multiplexing means we are performing the multiplexing operation with respect to the frequency domain. Okay, so regarding time division multiplexing, we will use in the digital communication while we are studying the pulse code modulation. That time we will use TDM concept, whereas in this particular chapter we will use FDM, because as I mentioned earlier, say for example, if you want to transmit 10 message signals or 10 voice signals, okay, in general the voice signal frequency range will be same. Okay, it exists from 300 Hz to 3500 Hz, but if you are transmitting all the signals as it is, then there will be interference. Okay, so just to avoid that one, with the help of different carrier frequencies, we will transmit each and every message signal centered around different frequency. After that, we can transmit those signals in the channel. In that way, we can effectively utilize the channel. Okay, and we can avoid the interference also from one signal to other signal. And whenever you are transmitting multiple signals, okay, in order to separate one signal to other signal, we will provide some range of frequencies. In that range of frequencies, we will never use that particular band of frequencies for any signal to occupy. Okay, we will just keep that particular spectrum simply ideal. So that particular spectrum we will call it as God band. God band just to separate one signal spectrum or one spectrum to other spectrum. Okay. And coming to the channel bandwidth and signal bandwidth, which one should be more, which one should be less? All of you can answer. This is a very simple question, but sometimes few students will get confusion. So that is the reason I have asked. So all of you please tell me, among the signal bandwidth and channel bandwidth, which one should be more? What is the relation? Always the channel bandwidth should be more when compared to signal bandwidth, because if channel bandwidth is more, then only you can transmit multiple signals. If signal bandwidth is more, then how you can transmit that signal in the channel? Not possible, right? That is it. Okay, so up to here, what are the concepts we have discussed? All the concepts related to amplitude modulation, that is first chapter. Now we are going to the second chapter, that is angle modulation. Chapter 2, angle modulation. So regarding the time domain signal, we already mentioned in the short, like AC into cos theta of t, where theta of t we can write it as omega ct plus phi. Okay, if you want you can write omega c as 2 pi f ct, like that. Okay, so from here instantaneous frequency, directly I am writing Fi equal to Fc plus 1 by 2 pi into d phi by dt. This is the instantaneous frequency, Fi equal to Fc plus 1 by 2 pi into d phi by dt. Okay, so here the difference between these two frequencies, that is nothing but frequency deviation, delta f equal to Fi minus Fc. And the moment you brought Fc left hand side, here left over term is 1 by 2 pi into d phi by dt. So that one also you can write. So based on the given data in the question, you can use any formula, 1 by 2 pi into d phi by dt. Okay, in order to find the frequency deviation, you can use this formula or you can use this formula. Now from here I am just writing one more relation, like Fi equal to Fc plus delta f. Fi equal to Fc plus delta f. Now you can observe here, in the frequency modulation, the carrier frequency is varying in accordance with the message signal. Okay, so if you want to get the maximum instantaneous frequency, here Fc anyway constant, the frequency deviation you should get maximum. Okay, similarly if you want to get minimum instantaneous frequency, then Fc anyway constant, same as it is, but regarding the frequency deviation you should get minimum. Regarding the frequency deviation you should get minimum. Just like earlier we have discussed, like AC into 1 plus mu, AC into 1 minus mu, in the similar way Fc plus delta f, you will get delta f min is nothing but minus delta f. Okay, next, similarly regarding phase modulation. Okay, whatever we have discussed here regarding frequency modulation, next you can put phase modulation. Okay, in phase modulation you will be having phi equal to Kp into m of t. Phi equal to Kp into m of t. So what are the formulas just now we have discussed? You can use similar formulas. Fi equal to, this formula if you are using instantaneous frequency, Fc plus 1 by 2 pi into d phi by dt. D phi by dt, where phi is nothing but Kp into m of t. Kp into m of t. So here Kp is the constant, we can keep outside. So Fc plus Kp by 2 pi into dm of t by dt. Dm of t by dt. So here if you want to get the maximum instantaneous frequency, that is possible when you are considering the differentiation term maximum. Similarly, if you want to get minimum instantaneous frequency, when you are considering this differentiation term minimum, like that. So similarly, regarding the frequency deviation delta, regarding the phase deviation, okay, delta phi is nothing but same. So here we are assuming that initially in a carrier signal there is no phase angle. Okay, that time whatever you got just now, when you are subtracting 0 from here, you will get the same thing, right? So from here you will get delta phi max, phase deviation max, is equal to Kp into m of t max, Kp into m of t max. Okay, so similarly here I am writing, if you want to get the maximum instantaneous frequency, so here dm of t by dt you should get max, okay. Now you can write the standard equation for FM, frequency modulation standard equation. For single tone you can write down S of t equal to AC into cos 2 pi f ct, AC into cos 2 pi f ct plus 2 pi kf integral m of t dt. This is the generalized equation. So in this generalized equation you can assume m of t equal to am cos 2 pi fm into t, am cos 2 pi fm into t you can consider, and you can perform the integration, and after doing few steps, okay, you will get the standard equation like this: S of t equal to AC into cos 2 pi fct plus beta into sin 2 pi fm into t, beta into sin 2 pi fm into t, okay, where beta equal to kf am by fm, where kf into am is nothing but delta f max divided by fm. So that means the maximum frequency deviation divided by the maximum message signal frequency, that ratio is nothing but the modulation index, and if the modulation index value is less than 1, which indicates narrowband FM, if the modulation index value is greater than 1, which indicates wideband FM. So based on the modulation index value, we are having the frequency modulation are of two types. One is narrowband, other one is wideband. So regarding narrowband, when you are considering beta value less than 1, so here you can consider like cos A plus B format, you just expand it like cos A cos B. Cos A plus B is nothing but cos A cos B minus sin A sin B. So that time, since we are considering beta value is very less when compared to 1, so that time cos theta is nothing but theta value you can consider like 0, cos 0 is nothing but 1, and sin 0 is nothing but 0. So that means cos theta you can approximate to 1 and sin theta you can approximate to theta. So from after doing like that, after doing few steps, you will get one standard equation regarding narrowband FM. So that one I am writing here. So regarding narrowband FM, the time domain equation S of t equal to, you will get the equation similar to your AM signal, but there will be slight change, okay, that I will discuss. First you can write down AC cos 2 pi fct, so whatever you are having regarding carrier signal term with respect to your standard AM signal, same term you are having. After that there you are getting AC mu by 2 into cos 2 pi into fc plus fm into t, right? Here in place of mu, there mu is modulation index, here in fm modulation index is beta. So similar equation you are getting AC beta by 2 into cos 2 pi into fc plus fm into t. Okay, so up to here it is same. Now there is a slight difference, okay. There what we have mentioned regarding upper sideband and lower sideband, the same signal amplitude you are having, but here amplitude wise same, but you are getting polarity wise opposite. Polarity wise opposite. Cos 2 pi into Fc minus Fm into T. So whatever the equation you got for amplitude modulation, standard AM signal, whatever the equation you got, similar equation you are going to get for narrowband FM. Okay, when you are considering magnitude wise, regarding carrier signal, whatever the amplitude you are having same, and regarding the upper sideband and lower sideband also you are having the same, provided if you are considering beta and mu both are same. Okay, so that means coming to the bandwidth, you will get same bandwidth 2 FM. So that means there are the similarities are there with respect to AM and narrowband FM. Okay, obviously when we had discussed about amplitude modulation, obviously that is a drawback with respect to bandwidth and with respect to power consumption, right? So obviously narrowband FM also will give similar drawbacks. Okay, so that is the reason in general we will use wideband FM when compared to narrowband FM. Okay, but here just for understanding you can write down bandwidth of narrowband FM. Bandwidth of narrowband FM is same as bandwidth of AM. Bandwidth of AM. So the moment you are saying bandwidth of AM, okay, AM and narrowband FM both are matching, so that means bandwidth formula will remain same. Okay, similarly the power required also will be remain same. PT equal to PC into 1 plus, there we have used mu, here we are using beta, that's all. AC into PT equal to PC into 1 plus beta square by 2. Okay, right. Next one, write down the standard equation regarding wideband FM. Regarding wideband FM, the standard equation you will get by using the Bessel function properties and by using the trigonometric Fourier series, etc. From there you will get the time domain equation like this. So S of t equal to AC into summation over n equal to minus infinity infinity Jn of beta into cos 2 pi into Fc plus NFM into T. Fc plus NFM into T. Okay, so you can observe by considering various n values starting from minus infinity to up to infinity, you are getting like, suppose for easy understanding, n value consider 0, you are getting only Fc. Okay, n value consider 1, Fc plus Fm, n value minus 1, Fc minus Fm, like that you are getting, okay, center frequency is Fc, and towards right hand side you are getting upper sideband frequencies, and similarly towards left hand side you are getting lower sideband frequencies. Okay, so theoretically speaking you are having infinite, when you draw the spectrum you are having the signal exist from, okay, which is having the frequency, the minimum frequency is what, Fc minus infinity times Fm into T. That means almost we can say consider minus infinity. Similarly, another frequency is Fc plus infinity times Fm into T. Okay, Fc plus infinity times Fm, that means almost we can consider plus infinity, right? So that means the spectrum exists from minus infinity to plus infinity, theoretically speaking. But whenever you are having any signal infinite bandwidth, okay, it is very difficult to pass that particular signal through any channel, because whatever the channels we are having, okay, so those are having limited bandwidths, but here signal bandwidth itself is infinity, then we have to provide more than infinity channel bandwidth, so it is practically not possible, right? So here, okay, there are some approximations are there, okay, so based on that approximations, theoretically we may say it is infinite bandwidth, but practically, okay, we no need to consider the entire, all the spectral components. If you are considering beta plus 1 upper sideband frequency components, beta plus 1 lower sideband frequency components, with the help of those spectral components, we are almost getting 99% of whatever the transmitted power is there, okay, that particular power is going to distribute here, okay. So that is the reason we are going to focus only that many band of frequencies. So accordingly, for practical applications, okay, theoretically you may be getting infinite bandwidth, but this particular signal we will pass through a selected band pass filter. With the help of that we will pass those selected band of frequencies. So with the help of that we are getting the practical bandwidth regarding wideband FM, okay. So coming to the power required for transmitting wideband FM signal, Okay, so when you are using the standard formula regarding the power calculation, so from there you will get, okay, from there you will get, okay, before that I will write another Bessel function coefficient, Bessel function few properties I will write. After that I will give the conclusion points. Regarding Bessel function properties, j minus n of beta is equal to minus 1 whole power n jn of beta. Okay, so that means if you are considering n value even numbers, so for all even numbers here this coefficient and this coefficient both will give same. Suppose n value if you are considering odd numbers, okay, that time you are getting negative. Okay, similarly one more property regarding Bessel function, summation over n equal to minus infinity to plus infinity, jn square of beta is equal to 1, jn square of beta equal to 1. And one more property, jn of beta decreases, jn of beta decreases as n increases. Jn of beta decreases as n increases. Okay, so as n value you are increasing, jn of beta is going to decrease. Okay, and one more important observation, j naught of beta is equal to 0. Okay, you can remember these beta values. Okay, for beta equal to 2.4, 5.5, 8.6, 11.8, like that you will be having. Okay, at least you try to remember these 3 or 4 beta values. Okay, so for these selected beta values, j naught of beta value become 0. Okay, j naught of beta become 0 means n value is 0, means you are getting only Fc. So at carrier frequency component, the signal strength you are going to get 0. So that is just like you are getting double sideband suppressed carrier, right? Whatever the power you are giving, the entire power is distributed to other sidebands. And here, while you are calculating the power formula, that time you will perform square term and then divide with 2. All the powers you will add. So that time when you are using this property, so summation over n equal to minus infinity jn square of beta equal to 1. So that time you are getting AC square by 2 only, common term. Okay, so that AC square by 2 is nothing but carrier power, right? That same power is required for transmitting this entire wideband FM signal, right? So you can write down, so the power required for transmitting wideband FM signal is equal to carrier power, that is nothing but AC square by 2. Coming to the bandwidth, so bandwidth equal to 2 into beta plus 1 into FM. So as I mentioned earlier, beta plus 1 upper sidebands, beta plus 1 lower sidebands we are considering. So together you are having 2 times beta plus 1 and multiple time FM, multiple of FM. Okay, so here regarding beta you can substitute delta F by FM plus 1 into FM. So now do the simplification, multiply FM with both, so FM will get cancelled, you are getting delta F plus here FM. Okay, so here the most important thing, whenever you are getting regarding FM signal, okay, in some questions interestingly they won't specify whether it is narrowband FM or whether it is wideband FM. Okay, so that time you have to observe the standard signal. Okay, just try to find out the beta value. If beta value if you are getting less than 1, it is narrowband FM. The moment you are getting narrowband FM, whatever the formulas you have used for standard AM signal, the same formulas you can use with respect to bandwidth and with respect to power. Okay, the moment if beta value is greater than 1, it is wideband FM. If it is wideband FM, you have to use these formulas. Okay, so this is the most important and interesting thing regarding FM. In few questions they won't mention whether it is wideband or narrowband, just to keep some suspense. Okay, you have to find out whether it is narrowband or wideband. After that you can use the respective formulas. Okay, so regarding generation of wideband FM, we are having direct method and indirect method. direct method and indirect method. So coming to the demodulation, here also we are having two methods. One is frequency discrimination method, another one is phase discrimination method. So here in this phase discrimination method, whatever the block diagram that we are using, that is nothing but phase lock loop. Phase lock loop. So with this we have completed regarding second chapter, that is angle modulation, right, regarding frequency modulation and regarding phase modulation. Okay, and the next chapter, that is receivers. Next chapter, chapter 3. Yeah, here this second chapter is also common for two branches, EC and instrumentation. Okay, whatever we have discussed so far regarding first and second chapters, so these two chapters are common for EC and instrumentation. Now the third chapter is only for EC branch. AM and FM receivers, this is only for EC branch. So when you are studying regarding receivers, so can you mention what are the receivers that you have studied? So I hope all of you can answer. We are having two types of receivers. One is tuned radio frequency receiver. What is the other one? Any guess? Tuned radio frequency receiver. Another one is, any guess? Super heterodyne receiver, right? Super heterodyne receiver. Super heterodyne receiver. So regarding AM, the operating frequency range. Regarding AM, the operating frequency range is 550 kHz to 1650 kHz. 550 kHz to 1650 kHz. Okay, whereas for FM, the operating frequency is, I hope all of you are familiar, 88 MHz to 108 MHz. 88 MHz to 108 MHz. So here in the tuned radio frequency receiver, okay, here the word tuning means we are selecting a particular station. If you are using AM receiver, we are selecting a particular AM station. If you are using FM, that means you are selecting a particular FM station, like that. Okay, you might have heard like 98.3 FM or 93 FM, etc. Right? Okay, so here tuned radio frequency receiver, okay, we will use here tuned circuit means we are selecting some particular station, right? So that means we can say that tuned circuit is nothing but band pass filter. Tuned circuit is nothing but band pass filter. And here tuning means we are changing the resonant frequency. Okay, here tuned means we are changing the resonant frequency. Okay, next coming to the super heterodyne receiver. Okay, in the super heterodyne receiver, we will be having image frequency concept. Okay, so before that you can write intermediate frequency. Intermediate frequency. So here the local oscillator frequency minus the incoming signal frequency. Whatever the incoming signal frequency you are having or signal selected station, okay, that one we are bringing down to some intermediate frequency with the help of local oscillator. Okay, so here the difference of these two is nothing but intermediate frequency. After that, this particular signal will be amplified. Okay, whatever the drawback is there in the tuned radio frequency receiver, with the help of super receiver we can overcome. Okay. So here you can write down for AM receiver, the intermediate frequency in general you will be having 455 kilohertz. In the questions they can give, okay, they can give 455 kilohertz or somewhere 500 kilohertz, etc. Okay, around this particular frequency they will give. And similarly for FM receiver, the intermediate frequency will be 10.7 megahertz. 10.7 megahertz. Okay, so here in the super heterodyne receiver, tuning means we are changing the local oscillator frequency. We are changing the local oscillator frequency. See here intermediate frequency already constant. In order to get that particular frequency, we will vary the local oscillator frequency. Okay, but here you may get, suppose with respect to the signal, okay, with respect to the signal, since this signal is low frequency, okay, so on the other side you will be having, or in other words we can say that greater than this particular signal frequency you will get for one more signal, okay, at that particular frequency also you may get same intermediate frequency. If you are getting like that with respect to the signal, that particular frequency is like image, okay, with respect to that signal, if that is the actual, and this signal will be like mirror image signal. Okay, so for the timing we have considered this particular relation. Here FL is greater when compared to FS. Suppose if FS is greater when compared to FL, then according the formula will change, FS minus FL. As I mentioned earlier, the frequency never be negative, right? Frequency always should be positive. That is the reason here we are considering difference of frequencies. Okay, whichever is smaller we are subtracting that one from larger. Okay, so here image frequency FSI equal to FS minus 2 times, sorry, FS plus 2 times intermediate frequency. Image frequency equal to the signal frequency plus 2 times intermediate frequency. Whatever the signal frequency you are having, just consider that one, and whatever intermediate frequency is there, multiply with 2. After that you can add these two. That is the image signal frequency. So this is your incoming signal frequency of a particular station. With respect to this signal frequency, this is mirror image, not mirror image. So that is creating disturbance. Why I am telling? Because with the help of this signal, when you are getting intermediate frequency something like 455 kilohertz or 500 kilohertz example, okay, the same frequency you are going to get even with the help of this one. Okay, because that time what will happen? FSI minus FL, because FSI is greater when compared to FL. That is the reason. Okay. So if you want to eliminate this particular image frequency before the intermediate, before the IF amplifier, we will use the tuned circuit. With the help of that, we can eliminate this image frequency. Image frequency can be suppressed by using a tuned circuit. Okay, we have to keep this tuned circuit before the mixer stage. Before the mixer stage, with the help of mixer stage, we are getting the difference of two incoming signal frequencies. Okay, so after this stage, if you are using that tuned circuit, there is no use at all. Before the mixer stage only, we have to use the tuned circuit so that we can eliminate if any high frequency signal is there, that we can eliminate. Okay, and we are having image rejection ratio formula. You can represent in short like this: image rejection ratio IRR. So this is nothing but I am representing with the letter alpha, symbol alpha. So alpha equal to square root of 1 plus q square into rho square, where q is the quality factor. Regarding rho you can write down here. So in general, when compared to FSI and FS, FSI is greater when compared to FS here, right? So that means you can write here FSI divided by FS minus FS divided by FSI. You are taking ratio of two frequencies, which one where we have to consider. Even if you are getting slight confusion, you can observe here. FSI is greater, right? FSI by FS minus FS by FSI. Okay. After doing this one, you are getting some value that you can substitute here. Okay. While you are solving the question, even if you are forgetting which one we have to consider, no problem at all, because anyway here rho square you are having, right? So that means obviously you will get positive. Okay, so up to here we have completed 3 chapters, right? So the first chapter is amplitude modulation. There we have discussed regarding amplitude modulation, DSBSC, SSBSC, and before discussing these modulation techniques, we have discussed the basic properties regarding Fourier transform, right? And then we have discussed frequency division multiplexing related also. With that, the first chapter is over, and then regarding second chapter, we have discussed angle modulation, that is frequency modulation, phase modulation, regarding that instantaneous frequency, frequency deviation, phase deviation, and then time domain signals with respect to narrowband FM and with respect to wideband FM. And one more important point, whatever the formulas we have discussed with respect to wideband FM, similar formulas will applicable even with respect to phase modulated signal, because there is a correlation between FM signal and phase modulated signal. That is the reason whatever the formulas you are getting for wideband FM signal with respect to the power required, PT is nothing but PC, then there is no issue at all. Regarding bandwidth, 2 into beta plus 1 into FM, right? So their beta value with respect to phase modulated signal, beta is nothing but delta phi, okay? So beta value, delta phi, both are same, that value you can substitute, and then FM as it is, okay? Coming to the receivers, we are having tuned radio frequency receiver and then superhetted and receiver, right? So regarding that operation you can focus, and whatever the formulas with respect to image frequency, image rejection ratio, just focus on these formulas, okay? You will get direct question, okay? So up to here we have discussed 3 chapters of communication system subject. So after the break, okay, so I'm giving 15 minutes break for all of you. So we are going to start the next session. So for that you are having one more link. So all of you can check the second link regarding communication system subject smart revision session in our IMS Gate Academy YouTube channel. So we'll start that session sharply at 3:30. Okay, we'll meet you all at 3:30. So thank you everyone.